Good morning and welcome to Lab 6, where we will be talking about probability and writing some of our own functions. So the Lab 6 HTML is on Blackboard. You can find it there. And as always, you want to open RStudio with your Geography 316 R project. So it should be in your Geography 316 folder. It has this .rproj file suffix on it. If some of you, your computers might not display it like this, it might just tell you the file type like this, the kind. So if you have something that says it's an R project, that's what you want to open. And by opening RStudio this way, you're ensuring that you're in the proper working directory so that when you read and write data and save plots, they're going to be in the right spot. And you can tell because if you come over here to Files, you will see all of your lab scripts here. So we will create a new R script, save it, it's your last name, and then Lab 6. This is Theo. All right, so let's see. All right, so as I'm sure you've gathered from lectures and videos that you've been watching, other things that you've come across before at statistics, the principles of probability in statistics are well illustrated by a coin toss. It's just a classic random variable. So there's some kind of structure to it, but you never know what the toss is going to come up with next because each toss is independent of all of the other tosses. So in particular, a coin toss is what is known as a Bernoulli trial. And so that is a special case of a binomial distribution, which means there are only two outcomes. In this case for us, it's heads or tails. Also, each trial, as they're called, is independent of all of the other trials. And the probability of either heads or tails remains constant. No matter how many trials you go through, no matter how many flips, that probability is not changing. And that's what's known as a Bernoulli trial. So we're going to simulate that in R. So that is done by using this R binom function. So this is in the same family of functions as the R norm that we've been using to take random draws from a normal distribution. This will take random draws from the binomial distribution. So I'm going to copy this out and we're going to run a trial in R. So we have our variable that we're creating here. We'll call it trial 1. And then we are going to run this R binom function. And it takes 3 arguments. N is the number of tosses. Size is the number of coins. So in this case, we're just flipping 1 coin. So we want to flip 1 coin 4 times. And then we want it to be a fair coin, which means we want the probability of either heads or tails to be equal. So here our probability is 0.5. So you can go ahead and run that line. And then in your environment, you can see your trial here. So this is a vector. It's not a data frame. And you can tell here because it's in the square brackets. So this time, all of our coins came up tails. It doesn't really matter if we call 0 heads or tails, but usually in these conditions, 1 is considered a success, and most of the time we consider heads a success. It really doesn't matter, but in this lab, we're going to go ahead and say that heads is 1, tails is 0. So let's run it again. You can see that this time we got 3 heads and 1 tail, 2 heads, 2 tails. Oops. All right, so I have you guys run that 4 times so that you have 4 variables. Let me just do this. So we'll run all those. I'm not having you set a seed here because it really doesn't matter if we all get exactly the same runs. And this kind of helps illustrate the principles of probability also. Now what we're talking about is probabilities in the long run. So the more times that you do this, the more different combinations that come up. That's where we get to things long-term probabilities, which here is that half of the time you're going to get heads, half of the time you're going to get tails. All right, so now what we want to do is calculate the number of heads in each of these vectors. So we're going to create 4 new variables. I was calling these trial 1 heads, trial 2 heads. And all you have to do here is take the sum of these trials. Because it's just zeros and ones, the count of all of the heads is just the sum of this vector. You can see that clearly here. We have 1 head, the sum of 0, 0, 0, and 1 is 1. 2 heads, that's the sum here. So let's run all these. And now we have 4 variables. This L indicates that it's an integer. We have 4 variables indicating the number of heads that we got in each run. So you can see and yours may be different. 1 run had 0 heads, 2 runs had 1 head, and then 1 run had 2 heads. So let's look at a histogram of that. So because, as we said in the last couple labs, ggplot requires a data frame to do the plotting, we are going to make a data frame with these 4 variables. And so we'll do that with this function tibble that we've seen before. Remember, that's just a special kind of data frame. So we open the function tibble and we say we want a column that we're going to call heads, and it's equal to these 4 variables. So these 4 variables are going to become 4 rows, and we need to put them all together in 1 vector, because remember that each column in a data frame is an atomic vector. So here we're saying, put all of these variables together as 1 vector, and then make that vector a column called heads in this data frame that we are creating called trials. Oops, and I forgot, you shouldn't forget, that always on the first couple rows of your script, you want to load the libraries that you're going to need. And so I forgot, because we didn't need the tidyverse library to run these functions. So we could actually just as easily load our library here. You just need to make sure and do it before you actually need any of the functions contained in that package. But I think it's a good process or a good, I'm losing my words, a practice, good practice to load it at the beginning of your script. So let's load the tidyverse. You can see all those packages are attached here. And now we can create our data frame. All right. This down here. So let's look at it. You can see it here in our data, trials. You can expand this. You can see that we have one column. It's an integer column. Here are the values. Let's look at it in spreadsheet form. So we have our one column heads. It's populated with the values, how many heads that we got in our 4 trials. And so now let's create that histogram. So again, we open our ggplot. We say the data that we want to use is our data frame trials here. Then you add on to that the geometry, so what kind of plot, which in this case is a histogram, and then our aesthetic mapping, so which variable in our data frame, which column do we want to be mapped onto the plot, which data do we want shown on the plot, and that is our number of heads. So let's run this and look at that histogram. And that is not super informative, I think. I think that if we had a lot more draws, so instead of 4 flips, say we had 50 flips, you know, then the number of heads could range anywhere from 0 to 50. If being that our coin is fair, most of them would cluster around 25. Sure, you can tell that's the basis of a normal distribution, that bell curve, right? I think that that would go a lot further to helping illustrate these ideas of probability. So what we could do is run all of this again, changing these ends to 50. But that kind of gets to be a pain in the butt. And it's also easy when you're copying and pasting and changing values like that to make mistakes and not realize that you've made a mistake. And so what we are going to do is we are going to create our own function. So the way that we've been using functions like sum and rbinom and ggplot and tibble, those are all functions. We can easily write our own function. And that's one of the cool things about R, is it's very easy to do. And in fact, that is why R is known as a functional programming language. So in order to make a function, we use the function. So let's make a function. And we'll do this one piece at a time because it may seem a little confusing at first, but really it's pretty simple. So first you want to create your function as a variable. That way you can use it repeatedly. So let's call ours coin toss. And then we have our arrow indicating assignment. We're going to say this coin toss is going to be equal to this function. So then we use the function. You can see how that turned blue right there because this is a special type of function. And then you open the parentheses. And so just like in the functions that we've used, our function will take arguments. So those arguments are the things that you specify to your function. I want you to use this data, or I want you to do something in this manner. Like when we give this argument to the sum function, we're giving it a vector. We're saying, okay, sum, here's the data that I want you to take the sum of. Or here in our rbinom function, we're specifying the number of draws, the probability, and the number of coins, right? So in our function, what we want to do is this, right? We want to run a trial, but we want to be able to easily vary the number of flips. So we're going to call this argument that we need to specify flips. We could call it anything we want because this is essentially creating a variable to be used inside of our function. But it's a good idea for anybody else who may come across your function that wants to use it. Also a good idea for your future self as a user of the function to give your function a name that's easy to understand what it does, and to name your arguments in a manner that it's clear what they are. So we could just name this X, N would be a little bit more clear, but I feel like flips is pretty clear. We want to specify the number of flips that are going to be used in our function. All right, so then within our function, we will create a variable, and this variable is only going to exist inside this function. So we're going to call it trials, and then trials is going to be this the output of our R binom function. So just like we specified it here, we can just copy that out. But instead of n being 4, n is going to be equal to flips, right? So you can see flips is here, flips is here. And then what we want as the output of our function is the total number of heads. So what we want is the sum of trials. And you see that we're not assigning this to a variable. That's because that's what we want as the output of our function. So what we're doing here is we're saying, okay, we're creating a function called coin toss. This function coin toss is going to take one argument, which is the number of flips that we want in this binomial distribution, right? And then from that, we want the total number of heads. So you run this line, and you can see now, where did you go? Whoops. You have to run it on the outside. There we go. Now you can see something different over here in your environment that you haven't seen before, which is this functions. So these are the user-defined functions. And so now that we have our coin toss function, we can use it. And the nice thing about RStudio too is it's going to pop up like this, just like the other functions do. But you can tell that it's your own user-defined function. And by the way, you don't want to name your own functions the same thing that functions in R are called. You wouldn't want to name your own function sum or rbinom or ggplot, because then it's going to overwrite those other functions and you won't be able to use them. So you want something specific to you. So coin toss, and you can even see here, we need the number of flips. So let's say 50 flips. And there, you can see that is the number of heads, is 27. Let's run it again. This time we got 20 heads, 23 heads. So pretty cool, right? And just the same as with other functions, you can also save this to a variable if you want. To say we call this trial 50 because we've got 50 flips. And now that value, the number of heads, is saved as a variable right here. So that had 26 heads. So pretty cool, I think. All right. And so I have you run that several times here. You know, so you can see that it works. You can see that it works fast, right? Here we flip a coin 1,000 times and it takes seconds. So we can also add a bit more to that function to make it a bit more useful. Because if we wanted to give this to ggplot again, we need it to be a data frame. And we would also like to run those trials many times, right? So this last time where we flipped our coin 50 times, we want to be able to do that 1,000 times, say, so that you can see how that distribution of the number of heads, as you increase the number of, trials, goes, whatever, the number of times we flip a coin 50 times and see how many heads, those experiments, as you increase the number of experiments, the distribution of the number of heads approaches a theoretical normal distribution. And we want to be able to see that visually. So we are going to expand our function so that it takes two arguments, the number of flips like we have here, but then also the number of trials. So how many times are we going to repeat flipping the coin however many times? All right. So let's come in here again and let's redefine our function. So we are overwriting it at this point because we're expanding on it. So again, we open our function. The arguments, we want the number of flips, but now we also want the number of trials. So you can see those arguments are separated by a comma, the same as they're separated by commas in any of the basic R functions that we've used that we did not create. So then the curly brackets, open your function. So everything that happens inside the function comes between these two curly brackets, okay? So now I'm gonna go over this slow because I don't want it to be confusing, and I think it's probably going to be, but we can get through it together because it is actually pretty simple. So, okay, in our function, we want to create a data frame where each row is the number of heads in our flips, right? So we're gonna flip a coin however many times, which is defined by this flips argument. And then each row in a data frame that has a number of rows equal to trials, because each row is a trial, in each row we want the number of heads from that trial. So let's start by creating our data frame. So Tibble, okay, and so we're going to say that in our Tibble, we're creating a column called trial. So this is the number of the trial. And the value of that column is going to range from 1 to trials. Because remember, this trials argument that you're going to pass into the function is going to be a number. So say we want 1,000 trials. You would put that here when you call the function like we did here, 1,000 trials. So this is saying create a data frame with a column called trial whose numbers will be 1 to 1,000 or 1 to 50 or 1 to 1,000,000. However many trials that you specify when you call your function, this is creating a data frame where the value of that first column trial is equal to 1 all the way to the number of trials, okay? And so remember our friends, the pipe here, this is saying, okay, take this data frame and feed it into the next function as the first argument. So we're going to use a new function here called rowwise. Oops. And all it takes is the single argument, which you're passing in through the pipe. So rowwise is operating on this data frame. And what rowwise does, sorry, I have a hard time saying that, is a lot like what group by did when we used it in, I'm not sure which lab, 5 probably, 4 maybe. So when we used group by, it grouped the rows into 3 groups based on another column, right? So we had group 1, group 2, group 3, and that's how we were able to plot them together, I believe, or do something to each group. This is similar, but it's saying instead of doing something to the entire data frame, we're going to do it row by row. So hence the name rowwise. We're going to take this operation and do it to every single row. So say something like we created a column that was called mean, and we just said, okay, take this data frame, create this new column called mean, and we want it to be the mean of our trials column. Every row would have the same number because we are just giving it the mean of the entire data set. But here we're going to do it individually for every row. So you can think of it as each row being its own group. All right. So we say, okay, create this data frame, and now we're going to do something to it row by row, so every row for itself. And what we want to do is create a new column in the data frame. So mutate, which we've used before, just means create a new column. We want to call that column heads, because this is going to be the count of the number of heads in each trial. And so we are going to combine these two lines of code right here. So instead of running this binomial function, which is our coin flipping, right? So this is saying, okay, flip the coin a certain number of times, and we're saving it to a variable here, and then we're taking the sum of that variable. We're just going to make that one line of code. So instead of putting trials here, where what trials is the output of this function, we are just going to take this function here, and then we are just going to take the sum of that directly, all right? So again, instead of making this equal to a variable and then summing the variable, we are just directly summing the output, okay? So you have your sum function on the outside, and then your binomial function on the inside, and then this last parentheses closes your mutate. So we're saying create a new column called heads that is equal to the sum of a binomial distribution characterized by a fair probability, so equally likely heads or tails, flipping one coin this number of times, which will be an input to our function. Okay, so let's run that. Sorry, again, you have to run it from the outside. There we go. So make sure that your cursor, when you run that, is up here. And so now let's see what it looks like when you run that function. So we called this, and you can call these variables what you want. They get a little bit long and clunky, but what I was saying here is this is a trial, a number of trials where we are going to flip the coin 50 times, 50 times, right? So each trial we're flipping it 50 times, and we're going to do 50 trials. And so same as with other functions, you could also specify it like this, you know, which is maybe a better practice, because then again, it's just kind of easier to read, easier to see what you're doing. So we're creating this variable where we're going to use our coin toss function. We want 50 flips per trial, and we want 50 trials. And so now you can see we do indeed get a data frame. We have the trial number here and the number of heads here. Pretty neat, huh? And so now that we have a function, we can use it over and over and over again, varying these in any way that we want. So, okay, say we want 500 flips per trial, still 50 trials. Easily do that. I mean, how long did that take? A split second? So now you can see the number of heads is very different because we're flipping it 500 times. But you can still see that generally these values seem to be clustering around 250, which would be our fair coin. Or say we want to increase the number of trials. We can easily do a whole bunch. What is that? 500,000 trials. In what, 4 seconds, 5 seconds? And so you can even see here, we have 500,000 rows, each with the trial number and the number of heads. So that's pretty powerful stuff, I think. So now what we can do, oh, well, we can even get fancier, right? Because really what we want to see is not just this data frame. I mean, we can kind of scroll through it and see what those numbers seem to look like. But as we've talked about before, one of the, I don't know, strongest types of descriptive statistics is data visualization. So we can look at the histogram of these values to see how it changes as we increase the number of trials. And so we can actually make that part of our function so that when you run the function, it creates the histogram automatically. All right, so we are going to use what we have here and just change it a little bit, okay? So because we want this data frame that we're creating to exist outside of our function, which you can see it doesn't right now. Here, let's clear all of this. Create this function again because you can see it no longer exists here because I cleared the environment. Here's our function, and oh, sorry, it does. Because we're naming it to a variable, it will exist outside of the function. But because we want it to create a plot as well, we need to return or produce two things from our function. And so we have to change it just a little bit. We need to make this into a variable. So save it as a variable. It doesn't matter too much what we call it because it won't have this name outside of the function after we run it because it's going to have the name that we assigned to it as the variable. So we can just call it dat here. And then we are going to add to our function this plot. And so this is going to be a bit different than what we've done too, because what we're going to do is instead of just running the ggplot function, we're going to save that as a variable as well, okay? So let's create our ggplot. The data that we want to use in that is dat, which is the data frame that we're creating here. So let's add to that our geometry, which is the histogram. And then the mapping, so the data that we want to see is going to be the number of heads, which is the column that we're creating here, which again is the sum of the flips, right? The sum of those binomial draws. And I'm gonna have you change the bandwidth to 0.5 because I played around with it. Oh, bin width, sorry, bin width. I played around with it, changing it, and I found that 0.5 produced the best looking histogram. As you can see, this one looks pretty goofy. And part of that is because these are integer values. So they'll only take 0, 1, 2, 3, never a 0.5. You end up with these big spaces here. All right, so in our function, we are creating a variable called dat, which is the data frame, and we're creating a variable called plot, which is our ggplot. And so now we need to tell the function what we want to do with those variables, how we want to be able to access them outside of the function after we run it. And so what we want to do is print our plot, right? And so print in this context just means create it. Usually when you print something, that just means kind of send it to the console. See here I said print 50 and it just wrote this 50. It writes it to the console. But when you're creating a function and you want it to produce a plot, you specifically have to tell R that you want to print it, which just means create it. So we want it to create our plot, and then we want it to return the data frame. And so return just means essentially create outside of the function, all right? And so because we have both of these in here, our function is going to both create the plot and give us the data frame, okay? So let's run that. So we're redefining our function. And so now, when we create this variable trials 50/50, where we have 50 flips and 50 trials, it's going to print the plot of this outcome, and it's also going to give us this data frame, and the data frame is going to be named this, because that's what we're creating as our variable. And so you can see that here, it creates the histogram, and then now we have this data frame that consists of, again, the trial number and the number of heads for that trial. And so now what you can do is increase the number of trials that you're giving to the function. So the number of times that you're flipping the coin 50 times. And each time it's going to create a histogram. And so you will be able to see, you'll be able to see how this histogram looks more and more and more like a theoretical normal distribution as you increase the number of trials. And that is the basis of frequentist statistics, which is the branch of statistics that we are learning about in this class. It's based on long run frequencies. So as you theoretically approach an infinite number of trials, you theoretically approach the normal distribution. And so probabilities that are used in statistics are based on this idea. Because if you just flip, let's say we only have 5 trials, that doesn't look very normal, right? 10. But then as you do more, you can see that it starts to take on that familiar bell-shaped curve. Bigger. And the more that you add, the more it takes on that symmetrical, familiar shape. And that's the basis of inferential statistics, being able to infer things about a population from a sample. It's all based on this idea, right, of long run frequencies. So I'm going to have you go through this, and like always, I want to see that code in your script to know that you have gone through all of these exercises. And so I also thought this would be a good opportunity to show you how to calculate z-scores in R. I know that's something that you've talked about quite a bit in class. So z-scores being a transformation of your original data points. So what you're doing is centering and scaling them, which means giving them a mean of 0 and a standard deviation of 1. And what that does is it takes the data from its original units and it puts it in units of standard deviations. So the z-score represents the number of standard deviations away from the mean a given data point is. And although it's changing the value of your data points, it's not changing those values relative to the other data points. And that's why it's a valid data transformation, is because you're doing the same thing to every one of your data points, they still maintain their positions relative to each other, which means that you're not changing the distribution of your data. All right, so to calculate z-scores for your data, which we're going to do on one of these trials that you run. So actually, I think it was 50 and 100,000, which is what we are here, but I'll name it the right thing. So you need to calculate both the mean, which we can just call M. So this should hopefully be familiar at this point. We want the mean of a certain column in this data frame, which you access with the dollar symbol. And so we want the mean of the number of heads in this data frame. So this is our trials of 50 coin flips, and we have 100,000 trials. So you can run that. And then you also want the standard deviation, which is SD, of this same column. Okay. And so if you'll recall, to calculate a z-score, you subtract the mean from a data point and then divide that value by the standard deviation. And we want to do that to every one of our rows in this data frame. Oh, first I have you create a ggplot like we did in the last lab, where you show the mean and then one standard deviation above the mean and one standard deviation below the mean. Just so you can see, or to drive home the point that calculating z-scores doesn't actually change the data relative to the other data points. So we open our ggplot. The data that we want to use is this trials, the 100,000 trials data frame that we created. We will add on to it our histogram geometry. And we want to map to that heads because we want to show the number of heads per trial. We have our nice bin width here, 0.5. And then remember that what we do is we add on to that a geometry of a vertical line that's defined by, oh, here I called this average, sorry. The x-intercept is the mean value, so average here, which is our variable, and we will color that red. And then we add on a vertical line where the x-intercept is the mean value plus one standard deviation. And then our next vertical line is the mean value minus one standard deviation. And we will color those blue. All right, and so you can see that here, right? So we have our mean value, and then we have one standard deviation above the mean and one standard deviation below the mean. And you can see that the mean really is around 25 right here. If you look at it here, it's 24.99. And so again, to talk about those long run frequencies, really what that means is as the number of trials approaches infinity, this mean, where the probability of heads or tails are about 50%, since we're doing 50 flips, that mean should be 25, right? This value of the mean will approach that true value of 25, but only in the long term, right? You have to do a lot of flips before you really start to approach that true value of 25. So now let's create those z-scores, which we'll do with the mutate function. Hopefully you guys could have guessed that. So here's our data frame that we've been using. So we want to redefine it because we're adding a new column. So we're saying take the original data frame, redefine it. So here we say take that data frame. Using this pipe, we're going to feed it into the mutate function. So this is saying we're going to mutate this data frame. So add another column to this data frame. We want that column to be called z-score. And we want that column to be equals to heads, so the column heads. So this is going to be for every row, the value of heads minus the average value divided by the standard deviation. So again, this is our z-score formula, and we are creating a new column with that z-score. So you can see here, now we have 3 variables. The trial number, the number of heads, and the z-score. So you can see that this makes sense, right? So this value of heads should have approximately a z-score of 0, right? Because the mean should be around 25. So 25 minus 25 would be 0, should produce a z-score of 0. You can see that these values that are below the mean have negative z-scores, and the values above the mean have positive z-scores. So now we're going to recreate this plot by using the z-scores instead, and then showing that mean of 0, and then the standard deviation of 1 and minus 1. And so I, again, had to play with the bin width because we're rescaling the data. So now our values aren't going to be between, 10 and 40. They're going to be between, something like -3 and 3. So this bin width ended up being more appropriate. So we will run that. And so you can see that it looks exactly the same, right? Except that our numbers are different here. All right, because remember, one z-score or one standard deviation, either above or below the mean is, I forget, but something like 60% of the data points, and then 3 standard deviations is around 2.96, I believe, contains 95% of all of your data points. And those are characteristics of the normal distribution. So, moving back and forth between these plots, the z-score and heads, they're exactly the same. You've just transformed the data points so that they're centered on a mean of 0 and have a standard deviation of 1. And so hopefully that you understand a lot of that from what you've talked about in the lecture portion. I just wanted to show you how to do it in R. So for your exercises, essentially you are going to run through exactly creating that function and then taking a variable number of draws, plotting those draws, and describing how that distribution changes, except it's going to be a little different because I want you to think about on your own how you are creating this function. So instead of using a binomial function, you're going to use that normal function. So you're going to take draws from a normal distribution. But what you're going to do is you're going to take the mean value of those draws. But so remember that the normal, this R norm, takes different arguments than this R binom, right? And so those arguments are going to need to be passed into your function as arguments. So with our R binom, or the coin toss function that we created, we had two arguments, right? The number of flips and the number of trials. For your function, you are going to need 4 arguments, because our norm, not only do you have to specify n, which is the number of draws from that normal distribution, you also need to specify the mean and also the standard deviation, in addition to the fact that you're going to want to specify the number of trials, right? So you're going to need to create a function say you want to call it norm function, right? And then function. And then here, you're going to need 4 arguments, right? So you want, say, the number of draws from that normal distribution, the number of trials, and then you also need the mean and the standard deviation. And so these are all variables that you are going to specify when you call your function. So like here, where we said we called our function with 50 flips and 100,000 trials, you'll be able to call your function with 50 draws, 100,000 trials. You want it to be drawn from a normal distribution with a mean of m and a standard deviation of this, right? So, like we specified this, you're just going to go through and essentially exactly copy this function, but change it, right? So instead of the sum, we want the mean of these values, right? And instead of a binomial, we want a normal distribution. And so then if you need to, go back to the previous labs or just in help here, you can look up our norm to see the arguments that it takes. So n, mean, and standard deviation. And so what you'll need to say here is, we want our mean to equal m and the standard deviation to equal standard deviation, right? And here, if you keep this the same, we want 1 to the number of trials. That's going to create all those rows in your data frame. And then, have your ggplot in here too. You may need to mess with this bandwidth depending on the values that you're getting. Just mess around with it, see what ends up looking best. It's essentially just following the same process. You're just changing the function. Just make sure and think about what you're doing in that function because we're defining that function in a different way. So good luck. I know that you guys can do it. If you're having problems, don't hesitate to reach out.